In this lecture, we shall study fluid statics. That means fluid at rest. What is a fluid? A fluid can flow. And we have gas and liquid. A fluid, in contrast to a solid, is a substance that can flow. Fluids conform to the boundaries of any container in which we put them. They do so because a fluid cannot sustain a force that is tangential to its surface. Now, what are density and pressure of fluids? Density is denoted by rho, and it is mass per unit volume. And the unit of density is kg per meter cube. Incompressible fluid if the density is constant, then the fluid is known as incompressible. Now, pressure. Pressure is the normal force per unit area of cross section. And pressure is denoted by P, and it is force per unit area. Unit of pressure is Pascal. The force is Newton, and area is meter square, so Newton per meter square. So this unit is known as 1 Pascal. And another unit of pressure, this is known as atmosphere. 1 atmosphere pressure, and which is equal to 1.05 into 10 to the power 5 Pascal. Okay, now we shall study the dependency of pressure in terms on depth of a fluid. pressure depends on depth of a fluid. Okay, now let us suppose that we have a container of a fluid in the form of a cylinder, and we consider a sample of the fluid a rectangular in form, and there will be a pressure on this top face of this sample. We call this pressure is P1, and there will be also a pressure on the bottom face of the sample. We call it P2, and the pressure on the opposite sides of the sample will cancel. And let us suppose that this depth is y1 and this is y2, and if we consider a coordinate system and the air fluid surface, for example, this fluid is a liquid, and if this is the origin, okay, and the positive direction is upward direction, okay, and the negative direction is downward direction. So the pressure on the top surface of the sample is P1, so the force is F1 is P1 into A, where A is the area of cross section of the top and bottom surface. Similarly, the force here on the bottom surface is F2, and F2 is P2 into A. And the pressure on the bottom surface is larger than the pressure on the top surface, because the bottom surface, it is the depth is higher than the depth of the top surface. So the force on the bottom surface will be larger than the force on the top surface. So the resultant force and this is P2A minus P1A, and if you take common, P2 minus P1 into A, and this upward force will be balanced by the weight of this sample of the fluid, and the weight of the fluid acts in the downward direction, and this is mass into acceleration due to gravity. Since the fluid is in equilibrium situation, so this resultant force F2 minus F1 will be balanced by the weight of the sample fluid. That is, this F2 minus F1 will be m into g, where m is the mass of the sample of the fluid. But this F2 minus F1 is this one, and mass of the sample fluid is density into volume, and volume is area of cross section into the height of the sample, which is y1 minus y2. So if we cancel a from both sides, then we have and this one can be written as P2 is equal to P1 plus rho G, and this is H, where H is the height of the sample fluid, and this is y1 minus y2. Now this relation P2 equal to P1 plus rho GH, you see, and this depth of this top face is y1 and depth of this lower face is y2, so y1 minus y2 is the height of this sample fluid. Now if we consider that the sample, the top face of the sample is just the air fluid interface, then we can replace P1 by P0, where P0 is the atmospheric pressure, so from this relation P2 is equal to P1 plus rho GH. If we have y1 equal to 0, y2 equal to minus h, then P1 we say okay P0, and P2 is P, then we have P equal to P0 plus rho GH. So we see that if we have the sample, the top face of the sample is the fluid air interface, and so the depth of the top face is 0, and the depth of the lower face is minus h, and then our pressure expression of the pressure is P equal to P naught plus rho GH. Thus we see that if this P is the pressure on the lower face, and the direction of the force due to this pressure will be the upward direction. The next topic we shall study is Pascal's principle. This principle says that a change in the pressure applied to an enclosed incompressible fluid is transmitted undiminished to every portion of the fluid and to the walls of its container. For simplicity, if we consider this type of arrangement, okay, and here say the area of cross section of this tube. This is a tube, and there is a fluid inside this, and we apply a force Fi here in the downward direction, and then we can obtain a large force F naught on the output end of the tube. And let us suppose the area of cross section is A naught here, and pressure is P naught here, the pressure is Pi. Now the area of cross section, the input end is Ai, so the pressure Pi is Fi by Ai, and similarly the pressure at the output end is force. This force actually will be balanced by some weight here we have not shown here. This is actually a hydraulic arrangement that can be used to magnify a force. That means we supply a smaller force Fi, we can get a larger force F naught. The work done is, however, not magnified, and is the same for both the input and output forces, as we shall see later. So P naught is F naught by A naught. Now pressure will be the same at this end and also at this end. So this pressure Pi will be pressure P naught, which will give you Fi by Ai is equal to F naught by A naught. From this, the output force is now from this relation you see if A naught is larger than Ai, then we see F naught will be much greater than Fi. So a small force can be magnified. If we now move the input piston downward a distance di. The output piston moves upward a distance d0 such that the same volume V of the incompressible fluid is displaced at both pistons. Then we can say that the volume is the area of cross section into height. That means the piston moves at the input end by di, which will be equal to the area of cross section A0 into d0. From this we can write down d0 is equal to ai by a0 into di. Now the work done at the input piston so is wi is fi into di, and the work done at the output piston so this input work is the work done by an external agent, and the output work, this is the work done by the system, by the fluid at the output end, and this is equal to w naught equal to f naught into d naught. Now if we substitute this, f naught is, we had, if you remember, fi by ai equal to f naught by a naught, and f naught is so a naught by ai into fi. So a naught by ai fi, and d naught, just we have found out this d naught is this ai by a naught di. So you see this ai and a will be cancelled out, a naught and n will be cancelled out, so we'll be left with fi into di, but this is nothing but the work done at the input end. So we have w naught equal to wi, which shows that the work w done on the input piston by the applied force is equal to the work W done by the output piston in lifting the load placed on it. The advantage of a hydraulic lever is this. With a hydraulic lever, a given force applied over a given distance can be transformed to a greater force applied over a smaller distance. The product of force and distance remains unchanged so that the same work is done. However, there is often tremendous advantage in being able to exert the larger force. Most of us, for example, cannot lift an automobile directly but can with a hydraulic jack, even though we have to pump the handle further than the automobile rises and in a series of small strokes. Okay, this is for today. In the next lecture, we shall study Archimedes' principle, and if we get time, then we shall discuss the molecular theory of surface tension.